In this video, I will discuss the inverse Laplace transform. So let me recall from the previous lecture that the Laplace transform can be thought of as a machine or a black box. Let me write here Laplace transform. The Laplace transform takes as input a function f of x here, input, and it produces a new function denoted by script L f of x or a capital F, and the variable for the Laplace transform is the variable s. In the previous lecture, we saw how to compute the Laplace transform of certain functions. The inverse Laplace transform is kind of the reverse of the Laplace transform. So the input for the inverse Laplace transform is a function of s, capital F of s. And when we have the input like that, the output is f of little f of x. So it go backward compared to the Laplace transform. And the inverse Laplace transform is denoted by script L inverse on top here of f of s. So you need to distinguish two things. For the Laplace transform, we begin with a function with the variable, independent variable x, and we get a new function with independent variable s. And the inverse Laplace transform goes the other way around. We need to know the inverse Laplace transform in order to solve differential equation, which we will consider in the next topic. Now, in order to determine the inverse Laplace transform more efficiently, we will need to use the table of Laplace transform. The table gives us formulas that we could use. So here's the list of a few formulas. We saw last time in an example that the inverse Laplace transform of 1 is 1 over s. And using the linearity of the Laplace transform, if we have inverse Laplace transform of k, then we have k times 1 over s, or the same as k over s here. And then inverse Laplace transform of exponential e to the alpha x is 1 divided by s minus alpha. And as usual, we have the condition on the independent variable s here. We didn't do this, but it turns out Laplace transform of polynomial of x is just 1 over s squared. But Laplace transform of x squared is 2 over s cubed. There are formulas for Laplace transform of x cubed or x to the 4, etc. But for now, we only need these two. Then we have Laplace transform of x times exponential. Say x e to the alpha x, then we have 1 over s minus alpha squared, etc. We also have Laplace transform of trigonometric functions, sine and cosine, like these things. Of course, when we are given formulas, we need to apply them correctly. For example, the formula here says Laplace transform of sine of beta x equal to beta over s squared plus beta squared. So, for example, if we look at Laplace transform of, say, sine of 2x, then the beta would be 2. And so we have 2 over s squared plus 2 squared, which is 4. That is the Laplace transform of sine of 2x. And for the Laplace transform of cosine 2x, we would have s divided by s squared plus 4, etc. These formulas will be given to you in the quizzes and in the test. So let's look at a few examples. Now from the table above, we see that the Laplace transform of the e to the 2x, which is the formula 2 over here. Laplace transform of e to the 2x will be 1 over s minus 2, provided that s is bigger than 2. 1 over s minus 2 for s bigger than 2. So when we take the inverse Laplace transform of 1 over s minus 2, Laplace transform goes from e to the x at e to the 2x to 1 over s minus 2. So inverse Laplace transform goes backward. We are given 1 over s minus 2. So inverse Laplace transform produces e to the 2x. Now similarly, from the table, we have that the Laplace transform of e to the negative x sine 2x exponential and sine. So let's look at the formula number 7 here. E to the negative x sine of 2x. Alpha is negative 1 and beta is 2. So we have 2 divided by s minus negative 1 squared. So first 2 divided by s minus negative 1 in parentheses squared plus 2 squared. This is the formula number 7. With alpha equal to minus 1 and beta equal to 2. And we can rewrite this as 2 divided by s minus minus 1 becomes s plus 1 square plus 4. So if we want to look at the inverse Laplace transform of the right hand side of 2 over s minus 1 squared plus 4, then we get back to e to the minus x sine of 2x. So in other words, if we want to look at inverse Laplace transform, we need to begin with the right hand side of on the table. Inverse Laplace transform, we are given function in s and we want to know the corresponding function in x. We look at the right hand side. Example 1 is very simple because we have straightforward answer. But to be more useful, we need to look at more complicated examples. Find the inverse Laplace transform of something more complicated, which is a fraction s minus 2 divided by s squared minus s minus 6. Now we have a more complicated problem. By looking at the table, you don't see any formula like this exactly would give us the answer. So in the way, we need to convert our problem into a simpler problem that we could use a table. And the tool to use is the old tool from your college algebra. Uh, Actually, you use that in calculus 2 as well, I believe. We use partial fractions. Partial fractions are useful here because it decomposes a complicated fraction like this into simpler fractions. And from the simpler fractions, we can use a table of Laplace transform. So to do that, um, as any problem with partial fractions, we need to factor the denominator first. Factor denominator. Numerator, we don't need to do anything now. We factor the denominator. So s squared minus s minus 6, we need to factor into s minus 3, s plus 2. And on top, on the numerator, we still have s minus 2. Now, partial fractions means that we, in the denominator, we have two factor s minus 3 and s plus 2. So recall from college algebra, we have partial fraction a divided by s minus 3 plus b divided by s plus 2. And we need to determine a and b. There's several ways to do, but a method I would recommend and I use very often is first we clear denominators. We clear the denominators by multiplying through by the entire denominator on the left hand side, which is s minus 3 s plus 2. So I multiply the left hand side. So over here I will think of this the left hand side here. This by the entire denominator, so we only have the numerator left. And on the right hand side, when we multiply the right hand side by s minus 3 plus s plus times s plus 2, we can cancel s minus 3 for the first factor, and we have a times s plus 2. And for the second one, we cancel s plus 2, so we have b times s minus 3. Now, we will use some special values of s and we determine the values of a and b. So we will set special values of s, and by special values I mean values of s that make one of these things to be 0. So for example, s equal to 3, that will be a special value because it will make s minus 3 here 0. So if we set s equal to 3, then we have 3 minus 2 on the left equal to a times 3 plus 2 plus b times 3 minus 3. And this here, of course, 0 is gone. We get 1 equal to 5a. Over here, we have a is 1/5. Similarly, we may set s equal to special value -2, and this time we will kill the factor a here, term with a here. So when s equal to -2, the left hand side becomes minus 2 minus 2 is minus 4 equal to a, as I said, will be 0 here. Minus 2 plus 2 would be gone, and then we have b here, minus 2 minus 3, which is minus 5. Solve for b. Minus 4 divided by minus 5, so 4 over 5, b. So we have the partial fractions. Let me rewrite here, s minus 2 divided by our original fraction, s squared minus s minus 6 is a is 1/5. 1/5 divided by s minus 3. 1/5 divided by s minus 3. b is 4/5 divided by s plus 2. Now, once we have simpler fractions here, we look at the inverse Laplace transform. Inverse Laplace transform of the entire fraction on the left hand side will be, by the linearity of the Laplace transform, we could split into 1/5, yeah, times inverse Laplace transform of 1 over s minus 3. Sorry, this is inverse Laplace transform. Plus 4/5 inverse Laplace transform of 1 over s plus 2, okay, by the linearity. So we get the coefficient 1/5 times. What is inverse Laplace transform of 1 over s minus 3? We need to go back to the table. We look for 1 over s minus 3. Among these formula, this is number 2 is the correct one. 1 over s minus 3. So the inverse Laplace transform will be e to the 3x. So we have 1/5. This gives us e to the 3x plus 4 over 5 times inverse Laplace transform of 1 over s plus 2. Then again, we need to look at the formula 2. At this time, alpha is going to be negative 2. Negative 2 will give us 1 over s minus negative 2, which is 1 over s plus 2. So we get e to the negative 2x. And this is the answer we're looking for. So from this example, you see that the key thing in determining the inverse Laplace transform is partial fractions. So if your skills are rusty, then you need to review partial fractions. But let's look at another example. 3. We want to find the inverse Laplace transform of this 2s squared minus s plus 3 divided by s squared minus 4s plus 3 times s minus 3. Now this is a complicated fraction. You may wonder why we have such a complicated fraction. It turns out that later on in the next topic, when we solve differential equations using Laplace transform, we will need to find inverse Laplace transform of such a fraction. Okay, so that's why we need to practice this here. So as before, we need to find the partial fractions. To do that, the first step is to try to factor the denominator. Let's rewrite the numerator. and factor the denominator. Here we have s squared minus 4s plus 3. We can factor as s minus 1 times s minus 3. But also we have another s minus 3 in the denominator that's already there. Now we need to combine the same factors into exponent. So we have s minus 1 and then s minus 3 squared. And what is the format for the partial fractions here? We look at each factor here. The first one, s minus 1, we will have a over s minus 1. Now, for the second one, s minus 3 squared, then the partial fractions has two terms. The first term begins with the same exponent 2 here, s minus 3 squared. But the next term, we need to combine all the lower powers of the denominator as well. Okay, so keep that in mind. When we have power 2, we need to begin with power 2 here, but we need to go all the way to power 1 right here. Now, clear the denominators by multiplying through by the entire denominator over there. So s minus 1 times s minus 3 squared. So on the left hand side here, we will have the numerator 2s squared minus s plus 3 equal to. On the right hand side, we multiply this denominator by each terms. So for the first one, we cancel s minus 1, so we have a s minus 3 squared. And then we have for b times s minus 1, and then for c plus c times s minus 1, s minus 3. So you should try to do the algebra yourself to see what's going on, but this is what it is. Now we're going to choose special values of s. So special values are values of s that make one of these factor 0. So say s equal to 1 is a special value. When we plug in s equal to 1 on the left hand side, we have 2 minus 1 plus 3, so we get 4 equals to a times 1 minus 3 squared plus b times 0, and then c times 0 as well. So the 2 are gone. And as a result, we have 4 equal to a times 4. So a equal to 1. Now, we can set s equal to 3. That's another special value. And on the left hand side, we have 2 times 3 squared minus 3 plus 3. On the right hand side, we have a times 0 square is gone plus b times 3 minus 1 plus c times 3 minus 1 times 0, so it's gone, and we get this is 18 equal to 2b, and so b is 9. Now we don't have any other special values of s to do, So we can set anything, say s equal to 0, some small values. When s equals 0, the left hand side is 3, the right hand side is a times s equals 0, so we have negative 3 squared plus b times negative 1 plus c times, look up here, s equals 0, c times negative 1, negative 3 times negative 3, negative 1, negative 3. So we have 3 here, and a is 1. Remember, we have above 1 times 9, b is 9, so 9 times negative 1 plus c times 3. So from here, try to solve for c. It turns out that this cancel out, so c equal to 1. Now we have 3 values a, b, c already. So let's rewrite this. Let me just write dot 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 because I don't want to rewrite the left hand side. It's a complicated fraction. I don't want to save some time. But I know that we have a over s minus 1 and then b over s minus 3 squared plus c over s minus 3. So all of that, a is 1, 1 over s minus 1, b is 9, 9 over s minus 3 squared, c is 1 over s minus 3. And so the inverse Laplace transform of whatever on the left hand side what we want to determine is the inverse Laplace transform of each the component on the right hand side. And by linearity, we could pull out the constant in the numerator. So 9 inverse Laplace transform 1 over s minus 3 squared plus inverse Laplace transform of 1 over s minus 3. Now we need to look at the tables and find the answer. First, for this, we should look for 1 over s minus alpha, like we did that in the previous example. One over s minus alpha, let's go back here. 1 over s minus alpha, that's just e to the alpha x. So using that fact, we have the first term will be e to the alpha, alpha is 1, so e to the x. And the last one is e to the 3x. Now for the middle one, it's something different because we have 1 over s minus 3 squared. So we look for 1 over s minus alpha squared. That will be 1 over s minus alpha squared. This right here. So we have x e to the alpha x. In our problem, alpha is 3. So over here, the answer is x e to the 3x. Oh, with the constant 9 in front. And this is the answer to our problem. The inverse Laplace transform of the given fraction is the sum of the 3 functions. Now we have seen exponential functions, but we haven't seen trigonometric. So let's look at another example with trigonometric functions. Example 4. Find the inverse Laplace transform of this 3s minus 2 divided by s squared plus 2s plus 5. So as before, in order to do partial fractions, we need to factor the denominator. But unfortunately, in this case, we cannot factor the denominator. The reason is, it turns out that the root of the denominator a complex root, so we cannot factor as we usually do. So in the case we cannot factor the denominator, we need to complete the square. This is a technique that you learn in college algebra. So what do we do when we complete the square? Let me recall the formula here that will be needed. That if you have s squared plus, let me see, like b times s plus b squared over 4, then we can rewrite as s plus b over 2 squared. This is the formula we will need. So what it means is, if we have s squared plus b times s, then we need b squared over 4 in order to have a complete square. And the complete square is given by s plus a half of b, parenthesis squared. So to complete the square for our denominator, s squared plus 2s plus 5. What we're gonna do is like this, s squared plus 2s. Now we're gonna split 5 here at the sum of two things. The first term is to make sure that we have a perfect square for the first three terms. So using the formula above, s squared plus whatever s here, we need whatever that is 2 times s, so we need that b squared over 4. So over here we will need b squared is 4 divided by 4 is 1, so we will need 1 here in order to have a perfect square. But well, 5 we have to split into 1 plus 4. The first three terms give us a complete square s plus a half of b, which is 1 squared plus 4. So I have mentioned b, but b is here. B is 2. This is a half of b. And this one here is b squared over 4, which is the same as a half of b parenthesis square. And that's how we complete the square. So now we rewrite the fractions. 3s minus 2 divided by s plus 1 parenthesis square plus 4. The partial fractions in this case would be a little bit different from before. What we're gonna do is like this. We will have two things. On top, we will have a times s plus 1 and then plus b. Denominator, we still have s plus 1 square plus 4. Now, be careful that we have a times s plus 1. S plus 1 comes from this. The reason we need to do partial fraction this way is that later on we can use a table, and I will explain when we get to that point. But let's determine a and b here. Well, clear the denominator. So we multiply both sides by the entire denominator right here. So that on the numerator we have 3s minus 2 on the left, and the numerator on the right we have a s plus 1 plus b. So as before, we need to determine the values of a and b, and there's several ways to do. You could do whatever you are comfortable with. But for me, I'm gonna choose special values of s. Say s equal to -1 here. I will kill this first factor. S equal to -1, the left hand side will be -5 equal to a times 0 plus b. So I get b equal to -5. Now next, I don't have any special value of s, so I can say set s equal to 0. And on the left we have -2, on the right we have a times 1 plus b. And I know that b is -5, so -2 equal to a minus 5, and so a is positive 3. Now rewrite the fractions. 3s minus 2 divided by s plus 1 squared plus 4. A is 3 times s plus 1, and then b is -5, so I have this. Now I'm gonna split it into 3 times s plus 1 divided by s plus 1 square, and the 4 I will rewrite as 2 square, and then we have 5 over s plus 1 square plus 2 square. Now you should have see what I'm aiming at. I want to use the formula, and let me recall the formula that involves trigonometric functions and exponential right here. We have for e to the alpha x and sine of beta x, I have beta over s minus alpha square plus beta square. So that's why we complete the square, right, to have the format s minus alpha squared plus b squared in the denominator. But for this formula, we need beta in the numerator. On the other hand, if we have s minus alpha squared plus beta squared in the denominator, and in numerator we have s minus alpha, then it will give us e to the alpha cosine beta. So I recommend that you take a careful look at these two formulas. Important to recognize how to use them. So go back. The inverse Laplace transform of 3s minus 2 over s plus 1 square plus 4 by linearity will be 3 times the inverse Laplace transform of s plus 1 over s plus 1 square plus 2 square and then minus 5 times inverse Laplace transform of 1 over s plus 1 square plus 2 square here. So using the table, what is the answer? We have 3 times. Or for the first fraction, we have s plus 1 over s plus 1 square plus 2 square. So this is s minus alpha divided by s minus alpha squared plus beta squared. So we're using alpha is minus 1 and beta is 2. Okay. So we will have e to the minus x cosine 2x. And then minus 5. Over here, we also use the same thing. Alpha equal to minus 1, beta equal to 2. But different formula. So maybe better I should try what is the formula we need to use. Going back here. For the cosine, that formula 8 s minus alpha divided by s minus alpha squared plus beta squared, formula 8. And for the sine, I have formula 7. But careful, formula 7 has the beta in the numerator here. So here we don't have the beta in. So we need to divide by beta. Divide the answer right here by beta. So let me make a note here. This is formula 8. This is formula 7. And for formula 7, we need to have the 2 in the numerator in order to use it. But here we have a 1, so we need to divide the answer by 2, meaning that it should be a half of the formula we get from 7, so minus x sine of 2x. So the answer is inverse Laplace transform of 3s minus 2 divided by s squared plus 2s plus 5 3 e to the negative x cosine 2x minus 5 half e to the minus x sine of 2x. And this is the end of this lecture.